These are the frequently asked questions for Algebra 2 for section 6.2A1. I'm going to start with number 12 and take a look at that one. And what we're always looking for, if it says multiply if possible, is does the index for one radical match the index for the other radical? So I'm taking a quick look here, and I'm seeing that both of those are 3's. That means I can go ahead and do that multiplication. So I would need to do 9 times negative 81, which is negative 729. Now if you're looking at that and you're thinking, should I know in advance that that's something good? Well, you should, because this was a 9 and this is an 81. The first one is 9 to the first, and then 81 would be 9 to the second. So if we have 9 to the first times 9 to the second, that, if we use our rules of powers, will have us adding the exponents, so it will definitely be to the third power. So this is a perfect cubed root, and it is negative 9. Number 13, again, before you start to do any multiplication, you check the indices. That's the plural for an index there. And we have a 4 and a 3. Not going to happen with this one. We can't do those. If the index does not match for each one of those radicals, we can't put them together. We cannot multiply them. Again, it's a closed system. Cubed roots are only multiplied by other cubed roots, fourth roots by other fourth roots. So this one, we just have to put not possible. And if it said explain, we would certainly put index does not match. And it absolutely has to in order for us to do that multiplication. Number 14, you take a look at that one, and they are both square roots. Looking at that index in there, and that's not a 1, it's just a mark to get you to look up there, because that index is going to be a 2. So we can multiply those two together, and that will give us the square root of negative 25. Problem is, that's not a real solution. We certainly should know that it is 5i, but that's not a real solution. And for number 18, we check the index. These are both square roots, so again, those are both little magical 2's there. And I'm going to put this one up above here so I have enough room to do it. So we go ahead and multiply 50 times 75 and get 3,750. Now, you always want to find the biggest, the largest number that has that index that you could use with this. With this one, I would think most people would try 25 right away. But then you realize once you do that, hey, I can divide by 25 again. That means that this is divisible by 25 squared, which is 625. So the square root of 625 times the square root of 6, which is 25 square roots of 6. And that would be simplified as far as we can go. Let me get this up to a full screen. Hopefully it'll give me a little more room to work as I get to the next page here. For number 21, it says simplify, and this one is a square root, so I thought, yeah, maybe I won't do this one, but it does have a variable in it, so I want to make sure I remember how to do that. You think of this as the square root of 50, and then the square root of x to the 5th. Well, the square root of 50 can be broken down to the square root of 25 and the square root of 2, so you have a perfect square. And remember, there's a little imaginary 2 for that index. Well, we use division to figure out what to do with the variables. So 2 does go into 5 twice, so we're going to have this x squared. Problem is, it doesn't go into it perfectly. So we're going to have a little ugly remainder here, and that little ugly remainder will be x to the 1st. Because 2 will go into 5 twice, which gives us this x squared piece, but it has a remainder of 1. Now this will be 5 square roots of 2, x squared, square roots of x. And now we pull all the nice stuff out front, and the nice stuff was the 5x squared, and we put all of the ugly stuff under the ugly radical symbol. 5x squared, square roots of 2x. And the last thing we need to do is consider whether or not we should use any absolute value bars here. So go back to the beginning and think about, did the person who wrote this problem restrict this in some way so that we shouldn't be thinking of negatives? Well, when they put that x to the 5th there, They were saying that they didn't care whether or not we put a negative or a positive x value into this problem, because when we raise that to the fifth power, that will give us either a negative or a positive value. So with this one, we don't need to worry about any absolute value bars. The writer of this problem did not restrict us to certain x values. They said everything was okay. Positives and negatives were good by using that fifth power underneath there. So no restrictions. Then we go to 22. And 22 is the cubed root of 32a to the fifth. We want to separate that into two cubed root statements, one about a number and then one about a variable. Now, when you're looking at 32, that's a pretty small number, so hopefully you're thinking, gosh, probably the only thing I'd be able to use there is going to be 2 cubed, which would be 8. So the cubed root of 8 times the cubed root of 4, and then for the cubed root of a to the fifth, 3 does divide into 5. It goes into it once, but it's going to have an ugly remainder of 2. 3 goes into 5 once, but with an ugly remainder of 2. Now the cubed root of 8 is nice. That's going to give me 2. Then I have this cubed root of 4 that I can't simplify any further. Nothing I can do with that. And I have an a and a cubed root of a squared that I can't do anything else with. So now it's just a matter of making this look pretty by putting the pretty parts out front, which would be the 2 and the a, and then putting anything that's ugly under that ugly radical symbol. So the cubed root of 4a squared. Now this one is going to be a cube root problem. So with this one, we don't need to worry about whether or not we have absolute value or not for this problem, which is kind of nice. You know, you don't have to go through the process of thinking about what did they intend when they wrote this problem. Now I'm going to run short of space. Smartboard's being kind of ornery, so I am not going to move that up. I'm just going to erase a little bit and make some room here. So we have the cubed root of 54 y to the 10th, which would mean we want to separate this into the cubed root of 54 and the cubed root of y to the 10th. So cubed root of 54, again, I'm thinking it has to be something pretty small. So we do 2 to the third is 8. No, that's not going to work here. But 3 to the third is 27, and 27 definitely goes into 54 twice. When we get to our variables, 3 goes into 10 3 times, but with an ugly remainder of 1. And now my cubed root of 27 is 3. Then I have the cubed root of 2, y to the third, cubed root of y. And finally, I pull together the nice stuff, which was a 3y to the third, the pretty stuff, and any ugly remainders are going under that radical, and that will be a 2 and a y. So 3y cubed, cubed roots of 2y. Don't need to worry at all about looking for absolute value because that was a cubed root problem. Remember, it's whenever we have those even roots that we have to go back and think, when they wrote this problem, was it possible that they were going to be working with negatives with each of those variables? With 24, we have the square root of 200, a to the 6th, b to the 7th. So we're going to go ahead and write that as a square root of 200, and then the square root of a to the 6th, b to the 7th, and we're going to remember that our index here is a 2. So for the square root of 200, that would be the square root of 100 times the square root of 2. And our little magical 2 out here for the index is going to go perfectly into that a variable and give us a to the third. No ugly remainder. But for the b, it's going to go in there 3 times, but have one ugly remainder to deal with. The square root of 100 is 10, so we have the square root of 2, a to the third, b to the third, square root of b. Put the nice stuff out front, and then under the ugly radical, anything that we were not able to simplify there. Now with this one, this was a square root problem, so we need to go back to the beginning and we need to see whether or not we have to restrict one of these to only positive values. So I go back up to this first one and I realize when they put the number in for a, it's going to be raised to the 6th power. Pardon me. So that means no matter if we put a negative or a positive in there, the A portion of this was going to give a positive answer. So I go down and I look at what I have for A in my answer, and it's a to the third. I'm going to need absolute value bars there, because if somebody says, for this problem, I want A to be a -1, then all of a sudden I have changed the intent of this problem. Pardon me. So what I have to do is say, you know what, only the absolute value of a to the third, because the person who wrote this problem said, by raising this a to the 6th power, that value that I get out of there is going to be positive for the a's. Now for the b's, they didn't have that thought, because that was to the 7th power. So if it's to the 7th power, putting a number in there, whether or not it's positive or negative, will give you either a positive or a negative. So we don't need to worry about doing any absolute value on that B. Then, number 25, right here, we would start by saying, all right, I need the cubed root of -250, the cubed root of x to the 6th, and the cubed root of y to the 5th. Well, the cubed root of -250, hopefully that had you thinking right away about the cubed root of -125. So we've got the cubed root of -25 times the cubed root of 2, cubed root of x to the 6th, cubed root of y to the 5th, and this is going to give me -5 cubed root of 2. I'll go ahead and divide this out now. That'll give me an x squared. 3 goes into the y to the 5th once with an ugly remainder. So, oops, I need to leave room for my cubed root there. With an ugly remainder of 2, because that was a 5. So 3 goes into 5 once with an ugly remainder of 2. Now let's pull all the pretty stuff together. -5x squared y to the 1st, and all the ugly stuff that was underneath the radicals that we could not simplify. And finally, we need to ask ourselves whether or not this requires absolute value. It does not, because we have an odd root up there. And it's only even roots that get that consideration of whether or not we need absolute value or not. Now for number 26, we'd separate this to the 4th root of 64, the 4th root of x to the 3rd, and the 4th root of y to the 6th. 4th root of 64 should have you thinking, gosh, that's a pretty small number. I'm probably looking at 2 to the 4th as something I can take out of that. And 2 to the 4th is going to give you 16, and 16 times 4 is 64. 4th root of x to the 3rd, nothing I can do with that. Pardon me, 4 won't go into 3 even once. But 4 does go into 6 once, just with an ugly remainder of 2 back there for that y to the 6th. So in the front, the 4th root of 16 is 2. We had the 4th root of 4, can't do anything else with that, or at least this book doesn't ask you to. Then we have the 4th root of x to the 3rd, and then we have a y, and the 4th root of y squared. And again, this book tells you to just leave that as it is. So I put the pretty stuff out front, the 2 and the y, and all the ugly stuff goes underneath the ugly radical symbol right there. Now, this one was a 4th root. So we have to go through and we have to figure out, when they wrote this problem, did they intend that x could come out negative, y could come out negative? So I take a look at my x variables and I'm done, because that was x to the 3rd. If somebody put a negative value in there, it was going to come out negative, so they knew that was going to happen, not a problem. However, that y to the 6th, that guaranteed that no matter what number they put in for y, it was going to come out positive. So if we go to our answer and we have any odd powers of y, we need absolute value bars. And there it is right there. Because we have to keep the writer's intent, which was the y variable will only give us positive values no matter what values someone uses for y. So in our answer, We have done that by putting absolute value around that y. That y will not be responsible for a negative portion of that answer. The other y is squared underneath the radical, so that one is not going to cause any problems at all. All right, on the next page, things got a little easier for a little while when you go to number 28. Those are both cubed roots, so you always check that index, and then you figure out what 6 times 16 is, and that comes out to 96. Then you start thinking of any perfect cubes that will go into that, and it might take you a little bit, but you get the cubed root of 8 and the cubed root of 12. And the cubed root of 8 is 2 cubed roots of 12. Now 12 seems kind of awkward because you're thinking, hey, there must be something else I can do with 12. But remember, we have to have a perfect cube that would divide into that evenly. The smallest one we have to simplify would be 8. And 8 does not divide into 12 evenly. So that one is done. Number 31. I'm going to start by going ahead and doing this multiplication because the index for both of these is a little 2. So the numbers out in front, 4 times 5, that's 20. That doesn't take any special consideration. Those are just numbers. We multiply them like we multiply all real numbers. Square root. The square roots that they have up there can be multiplied together. So I go ahead and do 2 times 6 is 12. X to the first, x to the first, x squared. And then I have this y squared that needs to be hanging out in the back there. And then what I need to do is I need to figure out whether or not I can simplify that. So it's 20 times the square root of 12, the square root of x squared, and the square root of y squared. And I realize the perfect square of 4 goes into 12 3 times. The square root of x squared, that's just x, and the square root of y squared, that's just y. So this is 20, and this is 2 square roots of 3x, y. Well, I already put the parentheses there, but remember, in algebra, when things are right next to each other, that means we're going to multiply. So I'm going to have 40, and then the other pretty part of this will be an x and a y, and then the square root of 3 in the back. So last thing to do here, because this does have an even root, is to check and see if they cared whether or not they had a positive or negative x or y value. So now I go back up here and I look at my x's and my y's, and right away I see the x's were to the first power, so they didn't care, because if you take a negative number and you raise it to the first power, it's going to be negative. They didn't care about the x's. However, they did care about the y's, and that's because this is a y squared. So no matter what number someone gave them for y, when it went into their formula, it was going to become positive. So I go to my answer and I realize I'm going to need those absolute value bars. That's the only way that I'm going to guarantee that what the writer intended, which was the y's will always be positive, will happen with my formula, with my simplified formula. Then, number 32, I'm going to start by going ahead and doing the multiplication because I checked the index, and that index is a 3 for both of those. So for number 32, 3 times 2 out in front would be 6. And then we would have the cubed root of 250, and y to the third and y to the fourth. To multiply similar bases, you add the exponents. Now, hopefully, as I start breaking this apart, you're thinking to yourself, oh, 250, I like that one. That's going to be 125 and 2. You're absolutely right. The cubed root of 125 and the cubed root of 2. And I might as well take care of that variable while I'm back there. 3 does go into 7 twice, but it's definitely going to have an ugly remainder of 1. So now I have a 6, and I have a 5. I have the cubed root of 2, which cannot be simplified. I have y squared, and I have the cubed root of y. So I will have 30, and then a y squared. That was the nice part, the beautiful part. And in the back, the cubed root of 2y. And this one, as I stop at the end, is a cubed root. I do not have to worry about any absolute value with that cubed root. Let me erase some space here and go after number 33. So I check on this one and I see that both the indices there are cubes, cubed roots. So I'm going to go ahead and multiply the negative times the 2 and then multiply everything underneath that cubed root symbol. Well, 2 times 15 is 30. X squared times x to the 5th is x to the 7th, because when you multiply similar bases, you add the exponents. Y squared times y, for the same reason, will be y to the 3rd. And now we want to start separating this one to see what happens. So we have negative 2, cubed root of 30, cubed root of x to the 7th, cubed root of y to the 3rd. So start thinking, any perfect cubes that are small enough to divide into 30, well, 27 isn't going to do it, 8 isn't going to do it. I can't simplify 30 at all this time. So this is about the variables. 3 does go into 7, it goes into it twice, but with an ugly remainder of 1. And then 3 does go into 3 for the exponent on the y, and that'll give us a y to the 1st with no ugly remainder. So now I'm going to pull the pretty stuff together. I have a negative 2, I have an x squared, and I have a y to the 1st. And then all the ugly stuff, the 30 and the x to the 1st, underneath the ugly radical symbol. So now, last thing I need to do is think about whether or not I need absolute value. This was a cubed root. I'm not going to need to check for that. It's only when we have even roots that we go back and check for absolute value. All right, one more to go, number 34. So I check for my indices and I see that they're both 4. That's great, but I've got some kind of obnoxious numbers underneath there. So I'm going to go ahead and multiply underneath the radical, though I have my 2 radicands there. 81 times 32 happens to be 2,592. And then, because I'm multiplying similar bases, I add the exponents. So it will be x to the 8th because 5 plus 3 is 8, and y to the 5th because 4 plus 1 is going to give me 5. Now I need to separate that, and this is just not a nice number here. The 4th root of 2592, the 4th root of x to the 8th, and the 4th root of y to the 5th. So hopefully you're going to your power chart and you're looking underneath that 4th root, and you always want to find the largest one that will go into it, and this time it's 1296. And 1296 times 2 happens to be 2,592. The 4th root of x to the 8th, you divide. 8 divided by 4 goes in perfectly. It gives you x squared. 4 does go into 5 for the y's. It'll go in there once, but it will have an ugly remainder of 1. So the 4th root of 1296, we use our table for that. That is 6. 4th root of 2, nothing else we can do with that. X squared y, 4th root of y to the 1st, which is just the 4th root of y. Now let's pull it together and put the pretty stuff out in front, the ugly stuff under the radical, and let's check this one to see if it needs absolute value. It is 4th root, so that means it is possible that we would need to put some absolute value symbols on here. So let's go back to the original that the writer of the problem had, and I notice x right away has an odd power. That means it could have come out to be negative. If I put a negative 1 in there, it's going to come out to be negative. The author of this problem did not care whether or not I had negatives involved. I go to the y's, and at first I'm thinking, oh, I'm going to need absolute value, but then I see a y to the 1st. Nope, they didn't care about the y's either. If they did, that would have been an even power. So that means negatives, perfectly fine in this problem. The writer did not have any restrictions, so I don't need to do any absolute value. All right, I did several of these. Hopefully that'll get you feeling like you're competent with this. Try the other ones, and we'll talk about what we need to in class.